in the group. So, so good morning again. Um, After a slight late start, but we can finish all we need to do anytime. So this course is mainly about PLCs mainly, but we want to talk about two things: PLC and then the second thing that we want to talk about, for briefly, is we want to talk about PLC programming, and we want to talk about finite state machines. But this is a small discussion. The majority of the time it will be this, the PLC programming. Since finite state machines require don't require so much hands-on lab work. Until everything clear up, we're going to start talking about finite state machines. We're not going to, hopefully by next week, we start talking about PLC programming. But today we're going to start talking about finite state machines. What you're going to need to download hopefully I'm spelling it right, Proteus or Multisim. So we're going to ask you to simulate a circuit. And for the PLC, we're going to ask you to download CX1. We're going to be using CX Programmer. I think it reached version 9 point something. And we're going to be using CX Design. So those are the two things that we're going to be talking about. So finite state machines has to do with designing a circuit, one method of designing a circuit to control a process. So it's dealing with a theoretical thing. If I want to design and build my own circuit, then we can use finite state machines to do that. And PLC programming is the known way to automate a circuit. So what we want to do, we want 3 assessment with the PLC. So we're going to give you a take home test. Well, yeah, we're going to be a take home test. We want to do a practical test and a small project. And for the finite state, so this is for PLC. So take home test is worth 10%. The final project, this is 10, the practical test is 20. This is for the finite state machine. is 30. And this is 40. So it's 4 different slots and the 4 different slots. If I'm able to, and I will change my mind during the course and just give you a multiple choice. Online multiple choice test, if possible. Okay, so so that is basically what we are going to be talking about. So, like I said, because we're in lockdown, I'm going to start with the finite state machines. Otherwise, I would have done it last, but let's deal with it first and try and get that out of the way. So, like I said, hopefully next week we will start talking about PLC programming when we hear of the situation, if it is going to be, if we're going to get worse or if we're going to get better.
You know, getting a better.
No, so that you're going to put me in a state of depression. So,
You know, getting a better. But manage your expectations. I expect the worst.
eh?
Manage your expectations and expect the worst.
Me too old for that now. Too old. Let's say it must get better than what. So we so if it is what we did one time, if it don't get any better and them only allow you out of your house for a 3-week period, and which day is this? On Wednesday. We just get asked to come 3 weeks, learn three different 3 week 3 weeks, 3 week stretch, wherever it is, we ask you to come, 12 o'clock, wire up, learn from wire up the circuit, do the test. If you finish, learn all the way what you need to learn in the first week. You can do the test same week and we're done. But it's over a 3-week period. So that is what I'm thinking that we may have to do to get the practical part out of the way, to know how to wire up the circuit and so forth. I at least get an idea of how to wire up the circuit and so forth. But we're going to ask you to do more simulation on your computer, and you need to get this CX programmer and CX designer out of the way. All right. So, but by the way, so it's so when Batman attack all over, we go hide under the bed and not come out of our house and stay in there until when? We have to come out of face, but some point, our face are at some point, Not true.
For real, sir.
Yeah, just stay under the bed and stay under the bed and stay under the bed and stay under the bed.
I don't mind saying my house still got cup,
Oh, well, you know what? Me get 20 pounds. Can't go walk upstairs again. So, anyhow, leaving that alone. So, we're going to do some preliminaries with finite state machine now. So the first thing we have to understand, flip-flop. So we did digital electronics.
Yes, sir.
Yes, sir. Yes, sir.
All right. So we know about J or rank. The JK flip flop. And remember anything about it?
Yes, sir.
All right, the thing that I would like us to remember is the truth table. J, K, the present value of the output. This is the output that we're looking at. So the n mean now, and the n plus 1 next value. So this is the present value. And this is the next value. You remember how this work?
Wait,
I put what the X mean. Let me ask questions. The question is not, this question is just to
you know, actually really don't care. Yeah, we call it.
so there is a X means don't care. So we put the X because we don't want to write the 0, 1, 0, 1 to make the table bigger. So we put an X. But it's really don't care. So the J is called set and the K is called reset. So when you are in this, when both J and K are 0, the output is the same thing as the input. So it is going to be, if it is 0, it's going to be 0. And if it is 1, it's going to stay at 1. The next part is called reset. You know, I wasn't seeing the whiteboard on before. I think just pop up, say, participant.
Yes, sir. Yes,
You're seeing it?
yes, sir.
All
Yes,
right.
sir.
So now, reset. So when the reset is high and the set is low, the output is going to be 0. When the set is high and the reset is low, output is going to be 1. And when the set is high, both set and reset are high. Then the output is the opposite of the input. So 0 becomes 1 and 1 becomes 0. I will call that state toggle. And they call this table characteristic table. All right. So I want to write down what is called an excitation table from that JK flip-flop. The excitation table put the Q and Qn plus 1 first, and then tell say what J and K ought to be to cause a transition. So if I'm at 0 and I want to remain at 0, what values of J and K? If I'm at 0 and then the next state that we go to is a 1, what values of J and K cause a transition? From a 1 and I want to go to 0 and a 1 and I want to go to 1. Okay, so let's work this out now. You know what? I'm going to put this over on the next. So excitation table. We say Q present value, and the next value, what value of J and what value of K can we use cause that. And then let me put back the characteristic table up here, J, K, N, Q, N plus 1, 0, 0, 1. Okay, so we say no. For each of these conditions, if I'm at 0 for my output and I want to go to 0 from my next output, then what are the values of J and K? Now, when we examine, there are always two values of J and K that will cause that. So I am at 0 now. So if I look in the table and I want to remain at 0, then look a rough work. Let me put it up where just a J and K values that we need. If I'm at 0, because Q value is presently at 0 and the next value is 0. So there is this in the table, 0 and the next value is 0. One of the values of J and K would be 0 and 0. But there's another one. If I'm at 0, and I want to remain at 0, then J and K can be 0 and 1. So write that down as if I'm at 0 presently, and I want to remain at 0, then J can be 0, because you see here J is 0, but K can either be 0 or 1, so put 0, don't care. By the way, we have seen an excitation table before, or this is the first time talking about it?
It's seen it before.
First time.
All right. So I'm asking because I know we're going through this and then everybody said then everybody we know this already, you know. All right, so make we go to the next one. So if I'm at 0 and I want to go to 1, so I'm at 0, I'm at 0, 0, so this is here, 0, and I want to go to 1, and this is also here, 0, and I want to go to 1. So the two values of J and K are J is 1, K is 0, and J is 1, K is 1. So we can write, so J is 1 and K is don't care. Because to get from 0 to 1, J definitely has to be a 1, but we don't care what K is. Okay, so the next one is 1, 0. So 1 and 0. 1, so here's a 1, and there's a 0 over here, so that's one condition. And then the next condition is here's a 1, and here's a 0. So for that now, the blue ones, this is 1 and 0, so J is 0, K is 1, and 1 and 0, J is 1, K is 1. So the table will have in K as 1 and J as 0. And then the final one is 1, and we want to stay at 1. 1, I want to stay at 1. So the first one is both of them being 0. And 1 Here it is. And we want to stay at 1. So that is 1, 0. So in that case now, it is, wait, this wrong here, we put 0 and 1. And system right rubbish on nobody there.
Yes, sir.
Instead of the down, the don't care
But
one.
I see it, you know. Yeah, that's what's with don't care. One.
1 and 1.
Another one.
Don't care on 1. Right.
Yeah, don't care on one.
Don't care on 1. Just make sure. Oh, don't care on 1. Right. Don't care on 1. And then
Don't care and 0.
and next one is don't care and 0.
0.
So this is my excitation table. So if I'm presently at a particular state and I want to go to the next state, then this is the excitation table. So the next step from that, still talking about something that you might have learned in digital logic. Because that is the segue, this is the segue to finite state machine. But so we're just taking it a step at a time. So design a circuit to count so I just put it up an arbitrary sequence. So design a circuit to count in the sequence 0, then 1, then 3, then 2, then 0, then 1, then 3, then 2. All right. So how is it that we go about doing that? So
There you with the truth table.
right. So we're going to, well, let me go back. First thing, we're going to write down the binary equivalent. So 0 is 0, 0, 1 is 0, 1, 3 is 1, 1, and 2 is 1, 0. All right, the binary values for each of these numbers, 0, 0, 0, 1, 1, 1, 0. So now, yeah. So you're going from, what is it, 0, 1, 3, 2. So you're going 0, 0, 0, 1, 1, 1, 1, 0. So you're going to make up your table. So the table is going to have your present value, the next value, and the J and K so I'm going to put x1 and x2, and then the next value is I'm going to put a star. No, that's going to sorry there. It change from x1 and x2. Just call it A and B. Put J, A, and K. A, B, and A n plus 1, B n plus 1. I just put a star, it's easier to see. So if I'm 0, 0, I'm going to put in all possible values that I can have for 2-digit numbers. 0, 0, 0, 1, 1, 0, 1, 1. This is 0, this is 1, this is 2, this is 3. So let me put back the excitation table. Now how the J and K did go again? Remember. 0x, 1, 0, don't care, 0, 1. All right. So now, so I make up a table that says the present value, and this is my A and this is my B. So present value, if I'm presently at 0, 0, what is it that I go to next? According to my table, if I'm presently at 0, 0, the next thing that I go to is 0, 1. So I put a 0, 1 here. If I'm presently at 0, 1, is here. Where do I go to next? Is 1, 1. So I put 1, 1. If I'm presently at 2, so this is 2 here. Where do I go? I go to 0. And if I'm presently at 3, where do I go to? I go to 2, which is 1, 0. Then I look and see. So now, let's examine the A's because we want to find out what are the J and the K values. We want to look and see what are the J and K values that will cause the transition for A. So if we look at the A here, this is 0 and it remains as 0. So what are the values of J and K that will say 0 and remain at 0? We're looking at our table, that's 0, is don't care, and X. What about 0 and 1? When we look in the table, 0 and 1 is 1, don't care. Transition from 1 and it's going to go to 0. 1 go to 0 is don't care, 1. And 1 to 1 is don't care, 0. And what about B now? 0 to 1, 0 to 1 is 1, don't care. 1 to 1.
Don't care, 0.
Don't care, 0. And then the next one is 0 to 0. That will be 0, don't care. The last one is 1. No, right. 1 to 0. So I don't care. And I 1. So this is my excitation table for the sequence that I have here. All right, so what is the next step?
K-Map.
So we have to do a, well, in this particular case, we don't really have to, well, we could do a K-Map. And then that is why we need to download the multi-sim. We did have multi-sim on my thing, and then we decided that I had to take it out from the computer, but we download it. Wait, I have it. I normally they take it off. So better. So the next step is just to do our Karnaugh map and simplify the circuit that we have. Just give me a second there. I'm trying to find something on there. One second. I'm trying to put back electronic workbench on the machine. So that but it doesn't work well on this machine. So every time I download it, I have to delete it. But for the purposes of the class, we try to download it again. All right. So let me go back here. All right. So we're gonna make it download that. So now we're going to use give me a second again. So if it downloads successfully and you have space on your machine, you can download it then. We're going to
What is a multi-sim?
in a multi-sim, but I'm downloading electronic workbench because it you can see the thing easier with electronic workbench. It doesn't
Multi-sim.
no multi-sim is better by far. Reason why I'm not downloading electronic workbench is when we are the teacher for the class, it easier to show what we're going to do with electronic workbench. But remember say electronic workbench was the predecessor. It's like the old version. It's like the gear car with gear.
Yeah.
But you learn
Yeah.
drive automatic. All right. So here's what we do with electronic workbench or multisim. Multisim is the same thing. I don't think that multisim. Yeah, the only thing
Will be control that mic.
all right, the only thing with that, so what we want you to do with multi-sim or electronic workbench, like I said, electronic workbench is this, is bring out the logic converter. Now with the logic converter, it is here. Problem. Try again. That was the problem it was given the last time. I can only tell you what it was supposed to do. It was supposed to bring up a truth table and I fill in the truth table and ask it to simplify it for me, rather than using but somehow it's not showing.
Oh, kind of like something that Logisim, but
Yeah, same Logisim. So you download Multisim, don't download electronic workbench type. Electronic workbench just show the thing a little bit clearer and quicker. Let's see where that things are work. Yeah. So that is going on. Yeah, we'll delete it and try load it back and see. So we have to do it by hand in the interim. But what I wanted to do was show you that with Logisim, or if you Proteus or like electronic workbench, you just bring out the truth table and simplify the truth table. So you don't have to use the Karnaugh map or anything like that. But this side set will give me trouble at this point in time. Let me bring it up back again. I'll see. One more second. Try it again. Okay. Um, all right. So when you click on it, it's supposed to bring out the truth table. And like I said, it works the same for Multisim. It's just that this is quicker and clearer. Yeah. So it has decided to annoy me. Let's try this again. All right, so we only have 2 things in our truth table. And then so when you thief things off of the net, and then we go back to what I was right. So each of these J, A, and KA would represent a truth table for us to simplify. So we would simplify. So the first one is 0, 1, don't care, don't care. So let me bring about the workbench again. Right there. Let me see. I don't know why it decided to check this much. What's going to say? No, they must learn how to use Karnaugh map. All right, so we'll put the truth table and then it's 0. Click on the next one, it would be 1. Or if you double click on it, it's supposed to change. Now you can just type in the X, 1, and then we simplify it. And you see the simplification. You see what I'm typing on the screen, the simplification is down here. It's just, that would just equate to B alone.
Yes, I'm seeing it.
Okay. So you will just click on the simplify, and then if you want the circuit, well, it will draw the circuit for you. It will tell you what, and it will give you the circuit with NAND gates only as well. So you put in your truth table, put in your 0, 1, and your X and your X, and it tells you so that is equal to B. So JA is equal to B. KA now. Let's put that in the table. So XX, write them down and simplify them one time. So XX10 and 1X0X and X0X1. So the next one is XX10, and so we simplify that, and that gives us B prime, B bar. So I can make it bigger on the screen. So I hope you're seeing it. The next one is 1X0X, so that is 1X0X, and that is A bar. And then the last one is X0, X1, X, X0, X0, X1, and that simplifies to A. So we'll just use the software and sort it out. And as you see, I just went on the net and did that in 2 seconds flat. Download the software. So no matter we knock on our map in the future, we can use other things to solve the problem. So
All right.
we have JA equal B, and then we have KA. The simplification is B bar, and JB is equal to A bar, and KB is equal to A. So now we are in a position to do the circuit. So it's 2 inputs. So let me just draw the circuit here. All right, so the JK flip-flop. All right, so we have that JA is equal to B. So we connect JA to B. We have that KA is connected to B bar. So we connect KA to B bar. We have that JB is connected to A bar. And then we have KB is connected to A. So that would be my circuit that would count in the sequence. So let's wire it up and see if it works. Just taking a picture of the circuit so we can go back to multisim and wire it up. All right, so we need two JK flip-flops. We need an A stable. So connect it up there. And now we need two of these. Like I was saying, the thing about multisim. Wait. Sorry, wrong. I probably told them the same. So we can get multisim, then electronic workbench will do just fine for the purposes of simulating any circuit that you would have designed. We say JA connected to P.
So isn't that the inputs? The output, sorry.
Yeah. Uh-huh. So just label them. Yeah, so these are my outputs. So JA is connected to B, and K is connected here, and this is connected here. This is connected. I don't remember if I have to ground these pins here. Let me see. Oh, change the frequency. 1 hertz. Zero. Where we go now? 0, 1, 3, 2. Okay.
Yeah, it's still working.
All right. So the next step from that is to connect it to one of these things here. And I always get them wrong. So so this is an experiment. All right. Like I said, I
It is
just
from the other end now.
I just can't remember which is the right place to connect. All right, so we'll connect this over here first, and this here second. And try again. All right, so that wrong too. The other end, like I said.
Yes, sir. For far. Start from the right.
This must connect here or the other one.
Yes, sir. That one.
Okay. So so this would be a circuit to follow a particular sequence. So we're going to up it a little bit now. And kind of up the problem a little bit for today. So let me so this is design a circuit. So we're doing this because the same principle that we're applying here, the same principle that we apply to any circuit at all. Any automation that we want to do, the same principle that we're going to apply here. All right, so we want to design a circuit, but it has a control now. So when x equal 0, it counts down, and when x equal 1, it counts up. So once again, we're going to make up our table. but this time our table is going to have X, A, and B. And we're going to list all the numbers going down to 8. Because remember now, this is still 0, 0, 0, 1, 0, 2, 1, 0, 1, 0, 1, 1. So, and this is A, and this is B, and this is my X. So X, we're going to list all of the possible sequences. Need more space. So we're going to have X, A, B, J, A, K, A, J, B, K, B. So we're going to list count and list all possible values of X, A, and B. All right, so when X is 0, that's the first 4, then you're counting down. So when you're at 0, you go to 3. Oh, so I left out the most important part. I left out the next state. So A, next state of A, next state of B. So when you're at 0, X equals 0, when you're at 0, the next state is 3, which is 1, 1. When you are at 1, the next state is 0. When you're at 2, the next state is 1. When you're at 3, the next state is 2. When X equals 1 now, so we're up here. And when you're at 0, the next state is 1. When you're at 1, the next state is 2. When you're at 2, the next state is 3. When you're at 3, the next state is 0. So we want to write down the JA and KA that will cause the transition from A to A star. Of course, I never remember the table yet, so I'm going to put it back up here. So 0, 0, 0, 1, 1, 0, 1, 1. All right, go now. Don't care. Right. 0 don't care. Yeah, 0 don't care. 1 don't care. Don't care 1. Don't care 0. Yeah. All right. So if we're at 0, and the next state is 1. If we're at 0 and the next state is 1, then it would be 0. Next state is 1. 0 and the next state is 1 is 1. Don't care. We're at 0 and the next state is 0. 0 and the next state is 0. It's 0. Don't care. Why do you flying through this? Are you following what I'm saying?
Yes, sir. Following, sir.
Yes, sir. Yes, sir.
Okay. Because I'm going through this faster than 0 and 0. 0 don't care. 0 and 1. 1 don't care. 1 and 1 don't care. 0.
Well, sir, I said 1 and 0.
1 and 0. Where it is? Yeah.
No, as in the one that you had one and don't care right before you have the don't care 0. The second to last one.
All right, yeah.
That'll be 1 and 0, sir.
Should be 1.
No, sir, not for that one. The one before that one.
This one here?
Oh, that one. Oh, yes, sir. Oh, sorry, wrong. Not my bad.
Oh, all right. 1 and 0. 1 and 0 is don't care 1. And now B now. 0 to 1. 0 to 1. 0 to 1 is 1 don't care. 1 to 0 is don't care 1. 0 to 1 is 1 don't care. 1 to 0. 1 to 0. 1 to 0 is don't care 1. Probably 4. 1, 2, 3. 1, 2, 3, 4. 1. Oh. 0 to 1. 1 don't care. 1 to 0. Don't care. 1. 0 to 1 is 1 don't care. And 1 to 0 is don't care. 1. All right, so just a little point here. We don't have these two is ones and don't care. So we can treat the don't cares as 1. So we can easily write that JB is going to be equal to 1 and KB is going to be equal to 1. We don't need to simplify nothing there. So. Because it's pure ones and don't care. So we can just treat the don't cares. Don't care mean we don't care. So we can just treat it as a 1. So JB and KB, that can just be high. All right, so just take a little picture so we can remember it when we see it. All right, so we're going to go to we're going to need all of these. Back to foolish start again. It seems like start from scratch. All right. Reload it again. Let's see. Okay.
Okay.
All right. So in this time now, let me we have A, B, and I'm going to put X for C. All right, so just remember that. A, B, and I'm going to put X for my C is going to be my X. All right.
Sir, that wouldn't correct, sir. A would have to be the X.
All right, so that, yeah, I agree with you. So A is my X, B is my A, and C is my B. So let me fill in the table for JA. JA, we take a picture. 1, 0, X, X, 0, 1, X, X. All right, so that is not A. So the A is my X, so it's not X, not B, plus XB. So I write that down. Not X, not B, plus XB. And then for the next one, KA of X, X, 1, 0, X, X, 0, 1. I get back the same thing. Yeah, I'm gonna try this side. Just to make sure. First one is 1, 0, X, X, 0, 1, X, X. Let's simplify that. And just check. Okay. And then the next one is X, X, 1, 0, X, X, 0, 1. All right, so the two of them is the same thing.
Sir, the one before was different. It did have not B as well. So it did have not A, not B, not C plus AC, I think.
No, man, I did change something to see if it changed.
Oh, okay, okay.
Because I was getting the two same thing for the two tables. So I said, let me change one thing inside there and see if a different thing come up. So a different thing come up. So the two of them is the same.
Okay, sir.
All right. So now, all right. So let me draw the circuit on paper before on. All right. So, all right, down that. JA and KA and JB and KB equal 1. So draw the circuit. So we have A, we have B, So all right, try it this way. So X and then we need not X. We only need X in at all. Oh yes, we need X. So it is going to be B A we need not X and B. Or get both J A and J A. Now we need X and B bar. So this is the circuit. All right, so I'm just taking a picture of it with my phone so that I remember what it looked like when. So I'm going to go back to Multisim and try to implement it. Let's see if it works. All right, so we need two JK flip-flops. We need two AND gates. Need an OR gate. Need a clock.
Not
From
gate as well. And not gate.
all right, so how am I going to do this now? Is that I'm going to have four ways to do this. I'm going to do it this way. I will use the battery, convert it to 5 volts. All right, so we're going to convert it to 5 volts. Oh yeah, we needed that. All right, I'm going to put in a switch. We'll put in that gate through. Not, not. Put in a switch. Switch. All right, so I need to put another 5 volt over here. All right, so what my circuit supposed to look like? Let's put in at the same time. Um, we need to take a picture, but I never take the picture, so give me a second. All right. Anybody else did remember what the circuit's supposed to look like? Yeah, we changed some of the cosmetic things in the meantime. So we change the space to X. All right, when I click this switch X, now we're supposed to, when I press X, it's supposed to change. All right, now if we go back and look back at the circuit. But it was cube. This is A. Well, you get the general point of what it is that I'm doing, right? So,
Yes, sir.
mm,
Um,
so it's just to build the circuit. But so what we're going to continue from there and talk about is
Yes, sir.
using the same principles that we did here today and design the electronic circuit. All right. I'm going to finish this, but we basically finish for the day. I will show you it next class, but I'm going to finish where I up. All right. So we're going to segue from this into using the same principles, dead same principles to do circuits that will control equipment. I will give you the first assignment next week. So you can start working on it using the finite state machine. I will send the assignment in the group. All right. So can finish and see if this work. We're going to finish this, but basically this is what we wanted to do for the day.
so the not X and B should be going to the
Not B,
not B and not X.
B and not X. Should I put the not X? Yeah, the B and not X.
So wouldn't the not X be constantly on the 5 volts instead of the switch?
No, So we're gonna. It will be constantly on the 5 volts. So and then B is supposed to be a part of that. And then it's supposed to be, so B and not X, and then the other one's supposed to be X and not B. No,
X and B.
so it should be not X and not B. Let's check out.
Yes, sir. Yes, sir.
Your life. So this will be not X and not B. And then it should be X and B. And then finally the G and the K should be 1.
Right. So something like run this as the you said the GNK was supposed to be 1, but I said the 1 connect to the
Oh,
clock
sure.
and the
All right. This is everything. There. All right. Just put this. Oh. All right. So when we switch X, so that's 3, 2, 1, 0. And then when we switch it, it goes 1, 2, 3. So it works. All right. So basically is 1 hour basic or couple minutes we take and put together this circuit. So one of the things that we can point out is that designing some of these circuits to run some of these equipment is quick and easy. And then what you do is send them away to get the printed circuit, and then you can sort out everything, all the rest of the electronics. But we are just focusing on the design of the circuit as it is at present. All right, so like we said, this was just the introduction, because we just use the counter circuit, but we're going to go and talk about designing circuits to implement other do other things for us. All right, so we'll stop in here. So next on Friday we talk about more practical circuit, but it's the same things we're going to do, but we're just going to add one feature called finite state, where we have to draw the diagram, the sequencing diagram for it. All right. All right. So stop in here. All right. But if you have what is it now? If you have multisim, fine. If you don't have multisim, then just do the quick and dirty thing that I do, download electronic workbench. All right. So all right.
All right, sir.
All right, so bless.
Yeah.
All right, sir.